Assume there's this army tank, as you can see. Let's say its mass is some 2000 kg, so 2 tons. And assume it fires a bomb or a shell whose mass is some 100 kg, and it fires the shell at some angle. Let it be. I'll give you the details. So this is the situation. So if the 100 kg shell is fired with a speed of, let's say, 50 meters per second at an angle 37 degrees above horizontal. Okay. See, firing happens by means of or through internal forces only. Okay. So internally, there will be a small explosion happening. A chemical will explode and it will push the shell in one direction. Now, if the shell gets pushed in one direction, the tank will get pushed in the opposite direction. So suppose this surface is perfectly smooth. Can one of you tell me what will happen after the bomb is fired? What will happen to the tank after the bomb is fired?
Or it will set into motion
In which direction?
towards the right.
Why will it go to the right? The bomb is fired to the right. Why will the tank go to the right?
Oh yeah, so it'll go to the left because it has to
Ah,
be opposite.
yeah, it will go to the left. See, action reaction pair, internal forces, no? They are acting on the bomb in the forward direction. Then the same internal force will act on the tank in the backward direction. Actually, they act at an angle like this. On the bomb, the internal force is this way. On the tank, the internal force will be this way. But the tank does not go into the ground. So due to its horizontal component, it moves to the left. Find out the speed of the tank just after the bomb is fired. Calculate speed of the tank after the shell is fired. Try this, all of you. Any answer? Okay, one of you tell me, why should the tank gain any velocity? Why should the tank gain any velocity? Like what gives it that velocity? Which force? Okay, listen all of you. As we discussed, it's the internal force, the force generated by the explosion, you can say. On the bomb, the force will act this way, so it starts moving that way. On the tank, the force will act in the exact opposite direction. Action reaction pair. Okay. Apart from this, their weights are acting. The tank's weight and the bomb's weight are there. And the tank also experiences a normal force from the ground. Okay. Now see, the moment the bomb is fired, this force F that acts on the tank, okay, it will tend to make the tank accelerate that way. Now the force F has a downward component. The force F has a downward component like this. That makes the tank press harder onto the ground. So what will happen? The normal force suddenly increases. It won't be equal to mg of the tank. Okay. Before firing, the normal force from the ground would just have been supporting the weight of the tank. But the moment the firing takes place, the tank experiences a force at an angle like this, which has a downward component. So the tank gets pressed onto the ground harder. Normal force has to support that. It suddenly increases. Fine. Weight of the tank is anyway there. Now, if you see, if you consider the tank plus bomb as one system, what forces act on it from outside? Their weights will be acting and normal force from the ground is there. Okay. Now the bomb is fired at an angle. We know with what speed it is fired. 50 meters per second. Tank can only move towards left. Tank is not restricted to move at an angle uh, along the angle at which the force F is acting. Tank cannot move that way. So it moves towards left because of the horizontal component of that force. It gains that velocity. Okay, and that velocity is what we need to calculate. That means we need velocity of tank in the x direction. Okay. Now you look at the forces acting on this system. As we discussed, their weights are acting and there's a normal force from the ground. Their weights and normal force from the ground, they're all in the vertical direction. Horizontally, they cannot influence the motion. So in this situation, you can conserve linear momentum in the horizontal direction. Vertical direction, it cannot be conserved because normal force here will be more than mg. And because normal force is more than weight, there is actually a net force in the vertical direction. So in vertical direction, linear momentum is not conserved. But horizontally, there is no force from outside. Okay, there is no external force horizontally. Means net horizontal force along the x-axis is 0. So you can do momentum conservation along the x-axis. Now the bomb has some momentum. Mass into velocity, 100 into 50, 5,000. But that 5,000 is not in the x direction. So one of you quickly tell me, how much is the bomb's linear momentum in the x direction if angle is 37 degrees? Make it fast. Actual momentum is 5,000 kg meters per second. Angle is 37. So what is the component of momentum towards right?
5,000, sir.
5,000 cos 37, correct. Momentum of the bomb towards right is 4,000 kg meter per second. Then the momentum of the tank to the left also should be 4,000, because initially before firing, the entire system was at rest. Total initial momentum of this system is 0. So finally also it should be 0, at least in the x direction. Okay. So horizontally, whatever momentum the bomb gains, opposite of that, the tank should gain. Only then the net momentum will be 0. Momentum is a vector quantity. One gets positive momentum, the other should get negative momentum, such that the total remains 0. Therefore, you can say that the momentum of the tank should be minus 4,000 kg meter per second, and you equate it to its mass multiplied with velocity. That's all. You get velocity of the tank as minus 2 meters per second. So the tank tends to move back with a velocity of 2 meters per second immediately after firing. Bomb is fired with 50 meters per second. Tank moves with a speed 2 meters per second. Usually friction will be there. It will easily bring the tank to rest. It won't move much distance. Okay. Is the solution clear to all of you? Any doubts in this? Okay. Next, consider this situation. Suppose there is a ball of mass m moving with a velocity v towards a wall. Okay. It strikes the wall perpendicular to it. Fine. Let's say it is going quite fast. You can ignore the effect of gravity and all. It strikes the wall. Now, usually when a ball strikes a wall, what happens? Anyone? When a ball goes and hits a wall, what happens?
Where it hits the wall and then it drops down.
Okay. See, sometimes it may rebound. Okay. And how much, to what extent it bounces back depends on the material with which the ball is made. You all know that. Okay. Let's say this ball is made of such a material that after striking the wall, after hitting the wall, it simply loses all its momentum. It comes to rest. Okay. You assume it sticks to the wall. Or if the wall is perfectly smooth, what will happen? It will simply start sliding down like this after it hits the wall. Okay. So you can assume something like this. The ball strikes the wall and comes to rest. Let's say all this happens in a time delta t. Okay. Now when the ball goes and hits the wall, definitely the wall will experience some force. The ball also experiences that force. Okay. I want you all to find out, calculate or derive the force exerted by the ball on the wall. Do this, all of you. When the ball, okay, it is given to you that the ball hits the wall and comes to rest. Means the ball loses all its momentum. And all that happens in a time delta t. Find out the force acting on the wall. So you have to think of how force is related to momentum. Any answer, anyone? How are you trying to solve this? Aishwarya, what can we do in this case?
Sir,
Okay. Huh.
Sir, as force is m into a and momentum is mass into velocity, I tried writing momentum as m into force into t by v, sir.
Okay, you tried writing force as mass into okay. Can you repeat what you said? Force is mass into acceleration. Okay.
Sir, and then I wrote m is equal to f by a,
Hmm.
and I substituted it in the momentum is equal to mass into velocity equation.
Okay, you have momentum is equal to mass into velocity. So you are saying m is equal to p by v, and you are equating that to f by a. So f by a is equal to p by v. But how will you get f from there? We don't know a acceleration.
Sir, I can write a as v by.
Okay. See, you may get the answer, but you have not used the correct ideas. A is not v by t. Acceleration is not velocity by time. Acceleration is change in velocity divided by time. Okay. In this case, it may work because the ball is losing all its velocity. So final velocity is 0, initial velocity is v. So change will become 0 minus v, that is minus v. So change in velocity itself is the initial velocity. So in this case, you will get the correct answer. But the idea you used is not proper. Okay. Can one of you tell me how force is related to momentum?
Force equal to dp by dt, sir.
Newton's second law, F net equal to dp by dt, correct. And average force is total change in momentum divided by time taken for that. That's all. That is what you need to find out in this case. Force exerted by the ball on the wall is same as force exerted by the wall on the ball. Action, reaction. Okay. Now what is happening to the ball? The ball undergoes a momentum change. Initial momentum of the ball is mv. After colliding with the wall, the final momentum of the ball is 0. We are not applying momentum conservation here. But when momentum of an object changes, there must have been a force acting on it. Force is responsible for change in momentum. Okay. So whatever force the wall is exerting on the ball, okay, by nature it will be a normal force. That normal force only would have caused this change in momentum, right? Okay. So what is the change in momentum of the ball? Final is 0. Initial is mv divided by how much time did it take? It's given to you in the question that it takes a time delta t. Therefore, the average force on the ball is minus mv by delta t. Why minus? Because it is to the left side. Then average force on the wall will be to the right. So it will be mv by delta t. Change in momentum divided by time taken. Here the change in momentum itself is mv because final momentum of the ball is becoming 0. Okay. So first I found out force, average force on particle or on the ball. Then on the wall it will be the reverse of that, negative of that. Is this clear to all of you? Any doubt in this?
Sir, in the end, why did you write it as mv by delta t? Isn't it supposed to be minus mv? Or is it because it hit the wall and then?
Minus mv by delta t is for the ball. Because on the ball, the force is to the left. For the wall, it will be plus mv by delta t.
Okay.
It's like all the momentum mv of the ball was imparted to the wall. So the wall is being given a momentum mv in a time delta t. Okay. Now consider this situation, all of you. Suppose there is a wall, and let's say we are firing balls continuously at the wall. Balls, bullets, whatever it is, you can consider it whichever way you want. Okay, let's say the gun is firing bullets at the wall. Each bullet, I'll write it here. Each bullet of mass m is fired with a speed v. Okay, and the gun fires n bullets per second. Okay, so if the gun fires n bullets per second, then the number of bullets hitting the wall also will be n per second. Okay, calculate the average force experienced by the wall. Try this, all of you. The difference between the previous question and this one is that in the previous question, you are specifically given the time in which the bullet loses its momentum. This time, you are just told how many bullets are fired per second. Based on that, you have to find out. And here also, you make the same assumption. Bullet stops or comes to rest after colliding with the wall. Okay, that assumption has to be made. Try this, all of you. N bullets are fired per second. Means in 1 second, N bullets will hit the wall. From that, you find out in how much time one bullet will hit the wall. Means after how much regular time one bullet will hit the wall. If you can find that out, then you can write the expression for average force. Try it, all of you. I got one answer as nmv by delta t. I got another answer as nmv. See, there's no delta t given in the problem, so you should not have a delta t in the answer. Fine. Listen, all of you. We want to find out the average force experienced by the wall. Now, what exerts force on the wall? The bullet that hits the wall exerts force on it. How much ever force one bullet exerts, the same force all the bullets are going to exert, because they are all fired with the same speed, they all have the same mass. Okay, and they are fired at regular intervals. So, do you all agree with this or not? Will all the bullets exert the same force on the wall or not?
Yes, sir.
They do. Now see, if all the students of a class score the same marks, okay, let's say 80 marks, all students have scored 80, then how much will the average score of the class be?
80.
80 itself. Okay, so if all the terms are same, then average will be equal to any of the terms. Here also, you are asked to find average force acting on the wall. If every bullet exerts the same force, then the average force on the wall is the force exerted by one bullet, right? So that one bullet force, if you find out, that is sufficient. Okay, now how we are going to do that? We know the mass of the bullet is m. It is moving with a speed v. That means it carries a momentum mv. But what it is doing, it hits the wall and comes to rest. The bullet comes to rest. Means all the momentum mv is lost. So per bullet, if you see, the change in momentum is mv. I'm only taking the magnitude. Okay, per bullet, the change in momentum upon collision with the wall is mv. It loses all its momentum. Okay. Next thing we need is the time. How much time does each bullet take to hit the wall? Now you are told that n bullets are fired per second. N bullets take 1 second. Then one bullet takes how many seconds? That is the question. You have to divide by n on both sides. Okay. So one bullet will take 1 by n seconds. That means if 10 bullets are fired in 1 second, that means each bullet is fired in 1/10 of a second. So if n bullets are fired in 1 second, each bullet is fired in 1 by nth of a second. That is the idea. That's all. So the time after which each bullet strikes the wall is 1 by n. Therefore, the average force experienced by the wall, change in momentum divided by time taken. The answer is nmv. Hope this is clear to all of you. You can ask if you have any questions. Okay. So questions like this are quite common. You may even be asked like, water is, what can you say, projected against a wall. How much force acts on the wall? Such questions can be asked. So remember, you have to see particle wise. One particle, if you know how much force it exerts, then you can tell average force exerted by any number of particles also. Okay. Next, the last part of this chapter, forces in circular motion. Now, we had discussed briefly about circular motion in the last chapter, motion in a plane. If an object moves in a circle, let's say the circle's radius is r. Assume the object is moving with a speed v. One of you tell me, when an object moves in a circle, should it be accelerating or not? Is acceleration compulsory or not? When an object moves in a curved path or a circular path, is it accelerating or not necessary?
Sir, it should be necessary.
Why?
Sir,
Like how do you?
because
Huh.
uh, uh, one thing is it keeps changing direction. That's there.
Yeah. Okay. Actually,
And
that's enough. See, for velocity to change, acceleration is necessary. Without acceleration, velocity cannot change. And velocity is a vector quantity. It includes magnitude as well as direction. While moving in a circle, excuse me. While moving in a circle, the particle's speed may not change, particle or object. Its speed may or may not change, but direction must change. At one moment, it will be moving this way. At another moment, it will be moving some other way. Direction change is compulsory. That means acceleration is compulsory for circular motion. And when I say circular motion, no, don't always, don't fix in your mind that it should be a complete circle. Okay. In fact, I should say motion in a curved path. Any curved path, fine, requires acceleration because direction of velocity has to change whether magnitude changes or not. Direction must change, so acceleration is compulsory. Now you all tell me, we had talked about components of acceleration. Suppose velocity is in this direction and acceleration is in this direction. We can resolve acceleration into two components. One component of acceleration parallel to velocity. What is this component called? What is the component of acceleration parallel to the velocity of an object called? Okay. You all need to keep revising. Okay. Component of acceleration parallel to velocity is called tangential acceleration. Can any of you tell me what it does to the object? Acceleration in the same direction as velocity, what does it do to an object?
It increases the velocity of the object, sir.
Ha. It can increase or decrease the speed of the object. It can make it go faster. If it's in the exact opposite direction, it will make it go slower. Okay. So tangential acceleration changes speed of an object. Okay. We can take another component of acceleration perpendicular to velocity. This is called radial acceleration. And what does radial acceleration do? Obvious. It changes direction of motion of the object. It makes it go away from the direction in which it is currently moving. Okay. Now, when an object is moving in a circle, speed change may or may not happen. So this is optional. But direction change must happen. This is compulsory. If this is compulsory, it means this is compulsory. Radial acceleration must be there. There must be acceleration perpendicular to velocity. There may be an acceleration parallel to velocity also. Okay. And acceleration perpendicular to velocity will automatically be towards the center of the circle, and we call it centripetal acceleration. Radial acceleration itself, because it is directed towards the center, is given the name centripetal. Okay, so radial acceleration itself is centripetal acceleration. That is compulsory. Okay, tangential acceleration, which changes the speed of the object, may or may not be there. Okay, that depends on the situation, but centripetal must be there. And we even discussed the expression for centripetal acceleration. I don't know how many of you remember it. It is equal to v square divided by r, where v is the speed with which the object is taking the turn, r is the radius in which it is taking the turn. So if speed is more, you will need more acceleration to take that turn. We had discussed all this. Okay, if an object moves faster, it requires more force to make it deviate sharply compared to a slow moving object. Requiring more force means requiring greater acceleration. So if speed is more, acceleration required will be more. And with radius, it is reverse. Smaller the radius. See, small radius means sharp turn. To take sharp turn, you need to give more force. Means smaller radius requires greater acceleration. And according to the formula also, it's the same. Radius is in the denominator. Smaller the radius of curvature, greater the centripetal acceleration. The acceleration required to take the turn. Okay, so this is the formula for centripetal acceleration v square by r. You can also write it as r omega square, where omega is angular velocity. We had discussed all this. V is equal to r omega. And this comes from L is equal to r theta. Okay, so for circular motion, centripetal acceleration or an acceleration perpendicular to velocity is compulsory. And as I said, not just circular motion, whenever an object deviates from its path, whenever an object goes in a curved path, that perpendicular acceleration must be there. And where does acceleration come from? Acceleration comes when force acts on the object. Now, if centripetal acceleration is compulsory to move on a curved path, it means centripetal force is compulsory. There must be some force helping it take that turn, some unbalanced force providing that acceleration and helping the object take the turn. Okay, the force, or I should say the net force towards the center of the curved path provides centripetal acceleration. Okay, and this force, again I should say, and this net force is simply called centripetal force. Okay, whatever is the force providing the centripetal acceleration, you call that as centripetal force. Simple. Next.
Sir, can you scroll up once?
Huh.
Yeah, sir.
Okay. Next, if speed of the object changes, there must be a tangential force also acting. Tangential force gives tangential acceleration. Okay. Now see, tangential acceleration changes speed. Now earlier when we discussed circular motion in a plane, we discussed uniform circular motion. Means circular motion in which speed remains constant. If speed remains constant, then tangential acceleration is not there at all. So till now we didn't consider tangential acceleration. But it's possible that objects move in curved paths with increasing speed and also with decreasing speeds. So there can be tangential acceleration, there can be tangential forces also involved. Okay. Now for radial acceleration, we have a formula, v square by r. What is the formula for tangential acceleration? Tangential acceleration is just dv by dt. That is rate of change of speed with respect to time. This is not velocity. This is only speed. Okay. That is the formula for tangential acceleration. Fine. We'll discuss all this in detail. You'll understand. When we solve problems, you'll get comfortable with all this. So centripetal or radial acceleration, the formula is v square by r or r omega square. Tangential acceleration, the formula is dv by dt, rate of change of speed with respect to time. Faster the rate of change of speed, greater the tangential acceleration. Makes sense. Okay. So the forces providing these accelerations are called centripetal force and tangential force respectively. Now, one of you tell me, let us discuss examples. One of you tell me an example of an object which executes circular motion. Any real life object which executes circular motion.
Sir, fan.
See, fan is a complicated system. Why? Because fan is not a, what can you say? It's a continuous distribution of particles. It will be difficult to write the force acting on a single particle of the fan. And see, the fan as a whole does not execute circular motion. It's some points of the fan which execute circular motion. So don't say fan. Fan does not execute circular motion. Fan is stationary. So can you think of any other examples? The object as a whole must move in a circle.
The Earth,
Earth around?
Sun.
Earth around the sun. Okay, reasonable. Actually, Earth moves in an elliptical path around the sun, but it's almost a circle. Let's consider it as a circle, not an issue. Let this be the path in which the Earth moves around the sun. Okay. Now, due to Big Bang or whatever, somehow Earth got its velocity. Okay. We believe it's from the Big Bang only. A large explosion took place in which some of these fragments became planets. Okay. Something exploded. We don't know what exploded, but the pieces that came out of that explosion, some of those pieces are the planets that we now live on. Okay. Let's say Earth is moving with a speed v in this direction. At that moment, it's in this direction with a velocity v. Now we know Earth follows a curved path like this. So when it is following a curved path, there must be, it must be having centripetal acceleration towards the center of the circle. And if there is acceleration, there must have been a force acting on it. Can one of you tell me what force acts on Earth in this direction? What force acts on the Earth towards the center of the circle in which it is moving?
Centripetal force.
No.
Sir, how, sir?
Gravitational force, sir.
Gravitational force. Okay, it's the sun's gravity which pulls the Earth towards the sun, and that pulling force is what helps it stay in a circle. The force here is the gravitational pull of the sun or gravitational attraction of the sun. Okay, I'm sure you all are aware of this. Now that force, the gravitational pull of the sun, is towards the center of the circle. So this itself becomes the centripetal force. This is the centripetal force. Okay, this is what I wanted to clear actually. Students tend to think that centripetal force is an additional force which acts on objects. No, centripetal is simply a direction. Okay, it's like saying, listen to this all of you and get this clear. Centripetal force is not an additional force acting on the system. Now, suppose there is a box lying on the ground. Okay, simply a box placed on a horizontal surface. If I ask you what forces act on it, what is your answer? Weight and normal force. Okay. Weight is the gravitational pull of the Earth. Normal force is the supporting force exerted by the surface. Will you say an upward force acts on the object? No. If I ask you what forces act on it, you won't say upward force, no? One of the forces acting on it is in the upward direction. But you won't say there is some other force called an upward force. Okay. So saying centripetal force acts on an object is like saying an upward force acts on an object. Because upward is a direction. Centripetal is also a direction only. Centripetal means something towards the center. So don't say there is a force called centripetal force acting on an object. No. Out of all the forces acting on it, some will be directed towards the center. That resultant force towards the center is named towards the center. That instead of saying towards the center, we say centripetal. That's all. So it's not an additional force acting on a system. Okay. In case of Earth revolving around the sun, the gravitational pull of the sun behaves as the centripetal force. Okay. Now moon also revolves around the Earth. Tell me, what is the centripetal force helping moon revolve around the Earth?
Earth's gravitational field.
Earth's gravitational pull. Okay. The gravitational force exerted by Earth on the moon behaves as the centripetal force. Okay. Can you all think of any other examples of objects moving in circles?
The electron
when you-
around nucleus.
Electron around a nucleus. Very good. Okay. Those of you who studied atomic structure must be aware of it. Or basic knowledge. We know that electrons revolve around the nucleus in an atom. Nucleus has protons and neutrons in it. Nucleus is positively charged. Electron is negatively charged. And we know that opposite charges attract. That force is called electrostatic force. Fine. So nucleus attracts the electron. And that force acting on the electron, that electrostatic force acting on the electron is automatically directed towards the center. So the electrostatic force, I should actually call it electromagnetic force, let it be. Electrostatic force between the nucleus and the electron itself is the centripetal force here. Okay. Rishi, you were saying some other example of circular motion?
Sir, when you hang a stone by a thread and like you rotate it, like
Okay. A stone suspended by a thread and or a stone whirled in a circle with the help of a thread. Let's assume this is happening in a vertical circle. That's possible. So assume there is a stone being whirled along this circle. I'm sure you all must have tried that. Stone ID card, whatever it is. Assume as it goes around in this circle, at one instant, the stone is at the bottommost position. Tell me, what all forces act on the stone? It is moving in a vertical circle like this. Okay, so what all forces act on the stone at that moment? Anyone?
Weight and centripetal force.
If this was a real class, no, I would have made you stand. I just told you centripetal force is not an additional force that acts on the objects.
Sir, weight and tension.
Weight and tension in the string, correct. Weight will be acting this way and tension acts along the length of the string. Tension acts this way. Okay, now see, tension is towards the center of the circle as you can see. And at this moment, weight is exactly away from the center of the circle. So tell me, what is the net force towards the center at this moment? How much is the net force towards the center? Okay. Consider this case itself, block resting on the ground. It's in equilibrium. If I ask you, how much is the net force in the upward direction? What is your answer? Or how much is the net force in the vertical direction?
0, sir.
Correct. Net force in the upward direction is 0. How do you do that? Force acting upward minus force acting downward. So N minus mg, which in this case is 0 because we know N is equal to mg. Similarly here, if I ask you what is the net force towards the center, you will take forces acting towards the center and you will subtract forces acting away from the center. That's all. So in this case, it is T minus mg. That is what behaves as the centripetal force. Okay, so centripetal force, as I said, it's not an additional force that acts on the system. The resultant of all forces towards the center is what you should call as centripetal force. So at this moment, the centripetal force is T minus mg. Okay, now we can consider another instant also. Let's say the stone is somewhere here. Now, at that moment also the forces acting on it are tension and weight. Weight as always acts in the vertically downward direction. Tension acts along the length of the string. Okay. Assume the string at this moment makes an angle theta with the vertical. Tell me, what force is acting towards the center of the circle? On the object or on the particle, what force is acting towards the center?
T minus mg cos theta.
Okay, you told the net force. I asked only towards the center. Towards the center, it is tension. And away from the center, this mg's component will be acting. There's a component of mg directed this way. Because this angle is theta, this becomes mg cos theta. So mg cos theta is acting away from the center. Therefore, the net force towards the center is T minus mg cos theta. That is what you should call as centripetal force. Okay, so see, centripetal force is not a new force that we are talking about. We are still going to consider the usual forces that we used to consider till now. Weight, normal force, tension, friction. These forces only we'll consider. Out of these, what is acting towards the center? What is the net force towards the center? We just name that as centripetal force. Okay, when an object moves in a curved path, that force is compulsory. There must be a net non-zero force towards the center. And see, we know acceleration in the towards the center, centripetal acceleration is v square by r. If centripetal acceleration is v square by r, it means centripetal force is mv square by r, because we know force is mass into acceleration. Okay, therefore the net force towards the center of the curved path should be equal to mv square by r. This is just Newton's second law. We are just writing net force is equal to mass into acceleration. So whenever you come across situations where objects move in curved paths, you can use this equation. So when an object is moving in a curved path, this is how you apply Newton's second law to that object. Basically, that is what we are learning now. So far, we have only discussed cases where objects move in straight lines, along the ground, vertically, along the incline. They always used to move in straight lines. But if they move in curved paths, no. You can write two different equations. One is towards the center of the curved path. centripetal force, net force towards the center is mv square by r. Next, in the tangential direction also you can write net tangential force is mass into tangential acceleration. So basically what I'm saying is, till now we used to apply Newton's second law horizontally, vertically. We used to take two components, x components, y components. Or if block is placed on an incline, we used to take components along the incline perpendicular to the incline. So what we are now looking at is, if object moves in a curved path, take components in the radial and tangential direction. That is what we are learning now. Radial direction, this is how you apply Newton's second law. Net force towards the center is mv square by r. Tangential direction, this is how you apply Newton's second law. Net force is equal to mass into tangential acceleration. Okay. Can you all think of any other examples of circular motion? Planets revolving, gravitational, that case we have done. Electromagnetic case we have done, electron revolving around the nucleus. Then tying an object with a tying an object with a thread and whirling it around, that we have discussed. Any other cases of circular motion or curved path? Any curved path motion that you can think of? Okay, consider this case of vehicle taking a turn on a road. Fine, assume there is a large ground playground and a person is moving in a vehicle along a twisted path, okay, turning right, turning left. So if an object is taking a turn, there must be a centripetal force involved. Okay, there must be some force acting in the radial direction. We call that as centripetal force. So you all tell me, on a flat ground, if a vehicle is taking a turn, which force do you think helps in taking the turn? Don't say centripetal. I'm asking what is the centripetal force in that case?
Friction, sir.
Friction, correct. In the absence of friction, it's not possible to take a turn on a flat road. So friction is helping us take a turn there. Friction provides the required centripetal force. Correct. Okay, we'll discuss all those in detail. We'll solve problems, you'll understand. Okay, consider this situation, all of you. Let us do calculations based on all this now. Object is moving in a circle. Okay, you know what forces act on it. It is moving in a vertical circle. Let's say, okay, assume its mass is m. It's moving with a speed v at this moment. When it is at the bottommost position, let's say it is moving with a speed v. Assume the mass is some 200 grams. The speed with which it is moving is 5 meters per second. And the length of the string is 2 meters. Calculate tension in the string. Do this, all of you. Particle is moving in a vertical circle. Calculate tension at this moment. Any answer? Okay, listen, all of you. Pawan, unmute, we'll discuss.
Yes, sir.
You are asked to calculate tension. Tension is a what kind of quantity is tension? What kind of quantity is tension? Like tension, normal, weight, ఇవన్నీ ఏంటివి? What are all these? Okay, anyone? Tension, normal force, friction, weight, what are all these?
Forces.
These are forces. What is taking you all so long to answer? Okay. So the question is asking you to calculate a force. And the only way we know to calculate force is by writing Newton's second law, F net equal to ma. We have to include this force in this equation. Okay. So you have to write Newton's second law in such a way that you include tension in the equation. Hope this is clear to all of you. Pawan, you tell me, at this moment, at the given instant, in which direction does tension act on the ball or object, whatever it is? In which
Vertically
direction?
upward.
Vertically upward. Tension acts this way. Fine. Is the object moving in a straight line or a curved path?
Curved path.
Curved path. Now see, whenever objects move in a curved path, listen all of you, from now onwards, you have to imagine the way in which the object is moving. If object is moving in a curved path, you have to think in terms of radial. See, this yellow dotted line is the radial direction. And this purple dotted line is the tangential direction. Tangential means along the tangent. So not just in this case, in any case, if an object moves in a curved path, from now onwards, you have to imagine radial direction, tangential direction. Now tension clearly is a force acting in the radial direction. If you want to bring that into the equation F net equal to ma, you will have to write the equation for centripetal force. Centripetal force equation includes the radial forces. Okay, so we are going to write centripetal force is equal to mass into centripetal acceleration, that is mv square by r. In this equation, we should involve tension, and automatically it will get involved. Okay, Pawan, tell me, at the given instant, centripetal means net force towards the center. Okay, at the given instant, what is the net force acting on the ball in this direction? How much is the net force towards the center?
Sir, T minus mg.
T minus mg, correct. Okay, mg is acting away from the center. T is acting towards the center. So the net force towards the center, because Newton's second law is net force is mass into acceleration. So net force towards the center, which is what you call a centripetal force, becomes T minus mg. And you will equate that to mv square by r. That's all. From there, you'll get tension. Complete this, all of you. Use this equation, T minus mg is mv square by r, and calculate tension. These quantities, if you want, I'll copy them. The mass of the object is given to you in the problem. The speed with which it is moving is given. Length of the string is given. The length of the string itself is the radius in which the particle is moving. So radius is also known to you. Complete this, all of you. Calculate tension. Okay. How much is it?
Sir, 4,500
4,500 watt. Newtons.
newtons.
I don't think it will be that much. Mass 200 raskunnava.
Sir, 4.5, sir.
Okay. So T becomes mg plus mv square by r. I'll take m common. M is 200 grams, means 0.2 kg. G is 10 in SI units. V square, speed is 5, 5 square is 25, divided by the radius is 2. 25 by 2 is 12.5. 12.5 plus 10, 22.5. Okay, yeah. This becomes 22.5 into 0.2. 22.5 into 2 is 45. 45 only, no? 0.2 will be 4.5. That much is the tension at that moment. Okay. Let's try another question based on a similar situation. Consider the same object itself moving in a vertical circle. Mass is 200 grams. This time, assume the particle is at the topmost point of the circle. And there, let's say it's moving with a speed 2 meters per second. It's not 5, it's only 2 meters per second. Length of the string is still 2 meters. Derive tension in the string at that moment. See, think carefully. First, visualize tension. Tension acts like this. Okay. Next thing to do is visualize the motion of the object. Object is not moving in a straight line, it's moving in a curved path. Whenever an object moves in a curved path, you have to think in terms of radial and tangential. And tension in this case is in the radial direction. So centripetal force equation can help you find out tension. That is how you come to the conclusion that you have to write the centripetal force equation. Today's topic is centripetal force. So you may directly apply, but imagine yourself looking at this question in your final exam. How will you get the thought that you have to think in terms of centripetal? Okay. There's a way to approach questions. Path is a curved path. Then you must think in terms of radial and tangential, centripetal, tangential. Okay. Do this, all of you. Any answer? I got one answer as 1.6 Newton. We'll see. Actually, it is possible that you don't get an answer for tension also in this case. I just randomly gave these values. It's possible that tension is 0. We'll see. Pawan, what equations did you write? How did you get 1.6?
Sir, tension mg, okay, and then direction actor, we have to add this in.
Okay, this time tension and mg are both towards the center. So the centripetal force equation will be written as T plus mg is equal to mv square by r. There are only two forces acting on this object, tension and weight. Both of them happen to be acting towards the center at this moment. So their sum should be mv square by r. That's all. So T becomes mv square by r minus mg. M is common into v square by r minus g. This becomes negative. Tension can never be negative because string can pull, string cannot push. Okay, you are getting a negative answer here, means the answer is actually 0. Okay, the answer for tension should never come negative, which means the answer is 0. There won't be a tension in this string at all. Now, how is that possible? Some of you may ask. Okay, listen. Let's say this is the fixed end of the rope. You simply lift an object, okay, to this height and you leave it. What will happen? The object will fall down. Tension will be 0. The object will simply fall down, right? So even if you give it a small velocity, what happens? The object is going to fall off like this. Tension becomes, the string immediately becomes loose. That is what is happening in this case. Okay. At the top of the circle, if you give only this much velocity, 2 meters per second, what actually happens is that the ball falls off into the circle. So the string becomes loose. Okay. So in this case, there won't be a tension in the rope at all. Okay.
Sir?
Yeah, tell me.
Sir, minus 1.6 అంటే downwards అని అలా తీసుకొచ్చారు అంటే vertical
No.
axis
See, we have already assigned a direction, downward direction. Manam downward, like considering it to be downward, we wrote the equation. And we are getting a negative answer. How can tension in the downward direction be negative? Okay, because we already took downward direction and we are getting negative answer. Okay. So for this direction, negative means the upward direction and tension cannot be in the upward direction. Strings cannot push. Ideal string cannot push. Okay, so here it does not mean that it is in the downward direction. Okay. Fine then. So today what we discussed is about the forces that must be involved in circular motion. Remember, not just a full circle. Whenever an object moves in a curved path, you have to think in terms of radial and tangential. What forces are acting in the radial direction you have to see. What forces are acting in the tangential direction you have to see. Radial forces provide centripetal acceleration. Tangential forces provide tangential acceleration. And for circular motion or curved path motion, centripetal is compulsory. Direction change is compulsory. Okay, so there must be a net force towards the center. And in many cases, that will help you find out the unknown forces and all. So we also discussed some examples of circular motion. Then in some cases, we found out the forces, one or more of the forces involved. Okay. Next class also will continue this. Next class will be on Monday. I'll send you a worksheet tomorrow. It'll have questions based on conservation of linear momentum and also questions based on circular motion. What forces are involved and how to calculate those forces. Okay. Now I want you all to practice problems. I want you all to revise the theory also. Okay, because some of you, like not some of you, you are not readily answering questions when I ask like this concept, tangential acceleration, radial acceleration is very important. From now onwards, very frequently you'll be coming across objects moving in curved paths. So you have to think in terms of tangential radial, get used to that. Okay. Okay then, thank you all. We'll continue on Monday.
Thank you, sir.
Thank you, sir.